Assalamu alaikum wa rahmatullahi wa barakatuh. This is Islamic College Oshogbo, Ss2 Chemistry. You are welcome to the next edition of our online class. If you remember, we have been looking at nitrogen and its compound for the past few weeks. Today, we are going to look at other compounds of nitrogen, which are oxides of nitrogen. Like you are aware, oxides are binary compounds of oxygen. Therefore, oxides of nitrogen are binary compounds of oxygen and nitrogen. That is, compounds that contain nitrogen and oxygen only. There are three commonly known oxides of nitrogen: nitrogen 1 oxide, nitrogen 2 oxide, and nitrogen 4 oxide. Although there are others, which are nitrogen 3 oxide, dinitrogen 4 oxide, and nitrogen 5 oxide. But the ones that are most commonly known and the more stable ones are nitrogen, the first three that we mentioned: nitrogen 1, nitrogen 2, and nitrogen 4 oxides. Let's take them one after the other. Nitrogen 1 oxide, which is also known as laughing gas, which it is called laughing gas because of the effect that it usually has when an animal inhales it, and it also has effects on animal, that is an aesthetic effect on animals, and that is why it is often used in minor surgeries, which we are going to talk about as the lesson progresses. But let's look at how it can be prepared in laboratory. It is prepared when ammonium trioxide is heated. But this reaction is highly explosive because of the high heat that is emitted during the reaction. Therefore, it is not safe to carry out such reaction in the laboratory, heating of ammonium trioxide. But like the scientists will always find a way around every situation in order to avoid the effects, the explosive effect it could have. A mixture of two compounds that can produce ammonium trioxide is heated, so that as the ammonium trioxide is produced, it decomposes gradually to form nitrogen 1 oxide, and in such a situation, the amount that will be produced at the time will not be too much to the extent that an explosion will occur. And that is why a compound of trioxide, maybe sodium trioxide, potassium trioxide, calcium trioxide, or any other trioxide, is heated with ammonium chloride, so that potassium chloride and ammonium trioxide will be produced as shown in this reaction that is used. Now, as the heating progresses, ammonium trioxide is heated, is decomposed to nitrogen 1 oxide and water. Though the reaction is also exothermic, but the effect is not enough to cause havoc. The diagram to show how it is prepared is what we have here. If you look at the diagram, you can see that it is collected over water, telling us something that the compound does not dissolve in the water upon which it is collected. But if you look well, you see that it is warm water that is heating, showing that it doesn't dissolve in warm water, because nitrogen 1 oxide actually dissolves in cold water to a large extent, but it does not dissolve in warm water, and that is why it is collected over warm water. You will recall that we have mentioned a compound in the past which dissolves in cold water but does not dissolve in warm water. If you can remember, that is hydrogen sulfide. Hydrogen sulfide also dissolves in cold water but does not dissolve in warm water, and that was also collected over warm water. Please take note of that. Now, physical properties of nitrogen 1 oxide. It is neutral to litmus. You remember this when we are treating oxides, neutral oxides. Some oxides of non-metals which are neutral. Among them is nitrogen 1 oxide, and there are two oxides of nitrogen like that. Nitrogen 2 oxide is also neutral to litmus, but we are So we're talking about nitrogen 1 oxide now. It is neutral to litmus. It is fairly soluble in cold water, but it's soluble in hot water. That is why it is collected over warm water. It's colorless with sweet taste and fairly faint pleasant smell, and that leads to a state of unconsciousness in the body of animals when you eat, and it is denser than air. Definitely you should be able to do that. You should be able to calculate the relative molecular mass of the gas. Once you calculate the relative molecular mass of the gas, compare with the relative molecular mass of air, you will discover that it is about 1.5 times denser than air. Here the relative molecular mass of air is 28.84, as we have known, meaning that its vapor density is 14.42. That of nitrogen 1 oxide is about 1.5 times of that. Chemical properties. Nitrogen 1 oxide, when heated to a high temperature of 600 degrees Celsius, gets decomposed to nitrogen and oxygen. Therefore, since you know that oxygen supports combustion, it means whenever a burning substance is placed in a gas there containing nitrogen 1 oxide, if the heat is strong enough to get the nitrogen 1 oxide decomposed, the burning will continue. And that is why nitrogen 1 oxide supports the combustion of many substances. The kindles a brightly glowing splint. But if it is not brightly glowing, it will not kindle it, because the heat will not be enough to decompose it. And it also reacts with many metals and non-metals by oxidizing them. So it is an oxidizing agent to many metals and non-metals to produce the corresponding oxide. As you can see here, when nitrogen 1 oxide combines with copper it forms nitrogen and copper 2 oxide. When it combines with phosphorus, it forms phosphorus 5 oxide, which is what? White fumes. Copper 2 oxide is black. Phosphorus 5 oxide is a white fume. Now it undergoes similar reactions with candle. You know, candle is a carbonaceous material, meaning that it contains mainly carbon. So when nitrogen 1 oxide combines with it to form carbon 4 oxide, and when nitrogen 1 oxide combines with sulfur, it also forms 4 oxide. Now you look at the use. The main use of nitrogen 1 oxide is that it is used in surgery, in minor surgery, especially in dentistry. And for surgery, it can also be used for surgery for animals, laboratory animals, when we need to carry out an anesthetic on them. I have told you that it is a mild anesthetic. Now nitrogen 2 oxide, which was discovered by Cavendish in 1770, as you can see on your screen, was first produced by electric spark. When electric spark passes through here, it is formed. We now know that what causes that is because there's nitrogen here, there's oxygen here. So during electric spark, the nitrogen combines with oxygen to form nitrogen 2 oxide. Even though the nitrogen 2 oxide is not stable, it will soon combine with oxygen to form nitrogen 4 oxide. But nitrogen 2 oxide itself is also a compound on its own, and it is prepared. It can also be prepared in laboratory when moderately concentrated triazole-95 acid reacts with some moderately reactive metals. You remember this on from our lesson on triazole-95 acid that we treated just before this lesson. That some metals, when they react with triazole-95 acid, they form nitrogen 2 oxide, and that is the equation you can see there. The reaction with copper with triazole-95 acid forming copper 2 triazole-95, nitrogen 2 oxide and water. Next is the diagram to show the laboratory preparation of nitrogen 2 oxide. You can see moderately concentrated, that is 50% triisolated 5 acid. That is when you have 50 cubic centimeter of triisolated 5 acid in 100 cubic centimeter of water, you get 50% triisolated 5 acid. This is poured on top of copper tunnels, which is reddish brown in color, and then you have a reaction. So at the end of the reaction, the the content of the flask here becomes bluish in color because of the formation of copper 2 triisolated 5. Then nitrogen 2 oxide is involved. You will see it is also collected over water, showing that it is not soluble in water. It's not soluble in water. And just look at the diagram, you understand how it is prepared. Now, what are the physical properties of this gas? It is colorless as well, but it is poisonous. And that is why it is not safe to prepare it in the laboratory except where there is film cupboard. You know that when a film cupboard is used to prepare poisonous gases in the laboratory, it is the safety cupboard that is used. So where there is no film cupboard, it is not safe to prepare this gas in the laboratory. It is slightly denser than here. Nobody needs to tell you that. Just calculate its relative molecular mass and compare it with that of here. So it is neutral, and it is neutral to litmus as well. I have told you the 2 oxides of nitrogen that are neutral to litmus are nitrogen 1 oxide and nitrogen 2 oxide. It's also soluble in water, like we have seen in its method of preparation. Chemical properties of nitrogen 2 oxide. Nitrogen 2 oxide is also reactive because in nitrogen 2 oxide, the highest oxidation number of nitrogen has not been attained. Therefore, whenever it has the opportunity to react, it will react. So when nitrogen 2 oxide is exposed to the atmosphere, it will combine with oxygen to form nitrogen 4 oxide. And this explains why the smell of nitrogen 2 oxide cannot be determined, because whenever you try to perceive the odor, as soon as you open it like this, it combines with here to form nitrogen 4 oxide. So instead of perceiving the odor of nitrogen 2 oxide, you will be perceiving the odor of nitrogen 4 oxide. So it is difficult to say that this is exactly its odor. And whenever it comes with metal, it is easily reduced to nitrogen. It means in that situation it will be acting as an oxidizing agent. It oxidizes copper to copper 2 oxide and itself reduced to nitrogen. But when it comes in contact with strong oxidizing agent, it acts as a reducing agent. With potassium tetraosomanganate 7, acidified potassium tetraosomanganate 7, it decolorizes it. It decolorizes it and becomes triisonated 5-AO. When it comes in contact with iron 2 tetraoxovate 6, freshly prepared, the solution becomes dark brown. In this case too, it also acts as an oxidizing agent. And the dark brown compound formed, that is a complex compound, is what is responsible for the brown ring in the brown ring text that we described during the last class, which is used in testing for trioxonitrate 5 ions. Nitrogen 2 oxide is stable to heat. So when heated, it does not get decomposed. But when phosphorus, when you have a brightly burning phosphorus inside a gas jar of nitrogen 2 oxide, it will decompose to nitrogen and oxygen, and the oxygen will quickly combine with phosphorus to form phosphorus 5 oxide. So this reaction is similar to the one that we have 4 nitrogen 1 oxide. Now coming to the next compound of nitrogen, and that's the next oxide of nitrogen, which is nitrogen 4 oxide. It is reddish brown in color, and it's always formed whenever any transuranidated 5 salt is heated. But it is more easily prepared from heavy metals. When I say heavy metals, I mean metals from calcium, magnesium, aluminium, zinc, iron, lead, tin, and copper. Whenever transuranidated 5 compound of any of these metals are heated, nitrogen 4 oxide is produced. If you remember our lesson on transuranidated 5 compounds, you will know that there are 3 exceptions to this. The non-heavy metals of sodium, potassium, when they are heated, they don't form nitrogen 4 oxide. They will rather form the dioxynitrate 3 compound. Also, the ammonium transuranidated 5, when heated as well, will not form nitrogen 4 oxide. It will rather form nitrogen 1 oxide and water. So these are the exceptions to the transuranidated 5 action of heat on transuranidated 5 compounds. Please take note of those things. Now, other reactions of nitrogen 4, and the other methods of preparing nitrogen 4 oxide is that when concentrated transuranidated 5 acid is added to a metal, nitrogen 4 oxide is also produced. Also, when a mixture of tetraoxosulfate 6 acid and a salt of transuranidated 5 is heated strongly, then we have nitrogen 4 oxide being produced. We have nitrogen 4 oxide being produced, as you see it in your notes. Now, diagram to show the laboratory preparation is what we have here. You will see that you have lead 2 transuranidated 5 being heated, and the mixture of gases, because there are 2 gases that will produce nitrogen 4 oxide and oxygen. So the mixture of gases is passed over a mixture of ice and salt. Since nitrogen 4 oxide is more easily liquefied, it will be liquefied here, while oxygen gas would continue its journey and be collected over water here. So once all the oxygen have been collected here, then we can easily get our nitrogen 4 oxide from here. So this is one of the methods of preparing nitrogen 4 oxide in the laboratory. Now, physical properties, like we have said, it is reddish brown. It has a pungent smell, and it's also poisonous. Remember, we said nitrogen 2 oxide is poisonous, nitrogen 4 oxide is also poisonous. It is acidic to damp litmus paper. Among the 3 now, it's the only one that is acidic. Nitrogen 1 oxide is neutral, nitrogen 2 oxide is neutral. Nitrogen 4 oxide is acidic to damp litmus paper. That is, it will turn damp blue litmus paper red. And it is soluble in water, readily dissolves in water, unlike nitrogen 1 oxide that will only dissolve in cold water but not in warm water. Nitrogen 4 oxide readily dissolves in water, and when it dissolves in water, it forms acidic solution. If it dissolves in water alone, it will form 2 types of acid, which we are going to look at when we get to the chemical properties very soon. Now, it is denser than here. That this is something we can also easily determine by calculating its relative molecular mass and therefore its vapor density. and it is also easily liquefied at 20 degrees Celsius. When the gas is cooled to 20 degrees Celsius, it will form a yellow liquid, which is a dinitrogen 4 oxide. We are going to look at that as we progress in the lesson as well. Chemical properties. The first of the chemical properties we are going to look at is its combustion. When the gas comes in contact with red hot copper, red hot iron, burning magnesium, burning sulfur, it will form the corresponding oxide and nitrogen. So it means it would oxidize the metals and the non-metals when they are being burnt. So it's also an oxidizing agent to metals and non-metals. Then when it reacts with water, it forms 2 types of acids. As you can see, trioxonitrate 5 acid and dioxonitrate 3 acid. But if it reacts with water in the presence of oxygen, it will form trioxonitrate 5 acid alone. As dioxonitrate 3 acid is not so stable, so even if you have dioxonitrate 3 acid combining with water and with oxygen, it would revert to trioxonitrate 5 acid. As an acidic gas, it also undergoes neutralization. Whenever it comes in contact with any base, it will react with the base to form salt and water only. As you can see in this reaction, nitrogen 4 oxide plus sodium hydroxide will form sodium trioxonitrate 5, sodium dioxonitrate 3, and water. These two are salts, and this is water. So forming salt and water only, showing that it is acidic. And when the gas is cooled from its fumic nature, when it is cooled to 100 degrees Celsius, it would start forming dinitrogen 4 oxide, N2O4. If this gas is continuously cooled, dinitrogen 4 oxide is also a gas, but when it is cooled to 20 degrees Celsius, it becomes a liquid, yellow liquid. So, and that process is called dimerization, because the gas nitrogen 4 oxide and dinitrogen 4 oxide have the same empirical formula, but they are different. They have different chemical formula and different natures. So this formation of dinitrogen 4 oxide from nitrogen 4 oxide is called dimerization. It means 2 molecules of the same gas combine together to form another substance. If dinitrogen 4 oxide is heated back, it will form nitrogen 4 oxide. So the reaction is reversible. Then when you have a mixture of nitrogen 4 oxide and nitrogen 2 oxide together, the two of them will react to form nitrogen 3 oxide. That is NO2 plus NO to form N2O3. N2O3, and that is what we call nitrogen 3 oxide. Now let's look at the next area that we need to talk about. This is nitrogen cycle. When we say nitrogen cycle, we are looking at the various ways by which the nitrogen from the atmosphere is made available for plant and animal use, and the various ways by which that nitrogen is returned to the atmosphere. So this will maintain acid and nitrogen balance in the atmosphere, and it will ensure that the amount of nitrogen in the atmosphere is relatively constant. The percentage of nitrogen here will remain relatively constant. How does this happen? Nature has made it such so that it is easy for nitrogen from the atmosphere to be converted to nutrients for plant use, and for animals to take up these plants for its own nutrition and give back the nitrogen to the atmosphere. It starts when there is electric spark in the atmosphere. It could be as a result of lightning. During lightning, the atmospheric nitrogen combines with the atmospheric oxygen to form nitrogen 2 oxide. The nitrogen 2 oxide formed quickly combines with more oxygen to form nitrogen 4 oxide. When rain falls, the nitrogen 4 oxide formed combines with water to form two types of acid: dinitrogen 3 oxide, dinitrogen 3 acid, and triosonitrate 5 acid. Dinitrate diosonitrate 3 acid and triosonitrate 5 acid, HNO2 and HNO3. But just like we have said, in the presence of oxygen, only triosonitrate 5 acid is formed, HNO3. This HNO3 combines with the soil minerals like sodium, potassium, or any other metal in the soil to form the triosonitrate 5 salts. The triosonitrate 5 salts will act as nutrients for the plant. The plant will take the triosonitrate 5 salt up for its own nutrients, which will serve as a nitrogenous fertilizer for it. And when animals eat such plants, the nitrate is converted as protein into the body of the plant, body of the animal. So when the animal excretes, when the animal excretes, it releases the nitrogen back to the atmosphere in form of urea, in form of sweat. Also, we have some bacteria in the root nodules of leguminous plants which can directly convert atmospheric nitrogen into nutrients for plant use. When such plant dies and decay, nitrogen is returned to the atmosphere. Also, we have some bacteria that we call nutrifying bacteria, which are capable of converting nitrates to converting ammonium compounds to nitrates, to soil nitrates. We have denitrifying bacteria, which can do the opposite. We have nitrogen fixing bacteria, like I've said, in the root nodules of leguminous plants, which can take nitrogen directly from the atmosphere. All these take place in converting atmospheric nitrogen for plant and animal use. But death and decay of plants and animal return nitrogen back to the atmosphere. The nitrifying bacteria return nitrogen back to the atmosphere, that is by converting ammonium compounds to nitrogen. this process or these processes of converting nitrogen to nutrients for plant and animal use and returning nitrogen back to the atmosphere ensures that the percentage of nitrogen in the atmosphere remains balanced. This will be the convenient point. We are going to stop our lesson today. Please watch the lesson again and go to your assignment portal to solve the questions there.